AI Transformation Institute, which is jointly recorded between UIUC as well as Berkeley. Seo-Taek broadly works in applied probability, machine learning, and communication networks. And he received many awards, including the 2015 Infocom Achievement Award, 2041 Sigmatrix Achievement Award, and 2019 IEEE Koji Kobayashi Computer and Communication Networks Award. And he also received several best paper awards from Infocom, Applied Probability Society, and WIOP. And he has served as editor-in-chief of IEEE Transactions on Network. Today, he's going to talk to us about crowdsourcing. So without any further delay, Shrikant, the floor is yours.
Thank you, Sibateja, for the kind introduction. Thank you for the invitation to give a talk here, and it's my pleasure to be here. So I'll be talking about crowdsourcing, an algorithm for crowdsourcing. So this is joint work with my current students, Seo-Taek and Saptarshi Mandal, and my colleague, Dimitri Katselis. So as an outline, I'll just give you a brief background about crowdsourcing and what is different about our model and solution, and give you some experimental results and give some conclusions. Okay, so before we talk about crowdsourcing, let's talk about supervised machine learning. So in supervised machine learning tasks, so for example, a simple example is you're trying to train a neural network to classify images as either cats or dogs. You have a lot of images of cats and dogs, and you want to train a neural network to classify them, right? So first, what you need is to train a neural network. First, you need to have labels. For each image of a cat, somebody should say it was a cat, and some people should have gone through it and then identified something as a cat or something as a dog. For example, +1 could be a cat and -1 could be a dog, right? And where it is useful beyond the cat-dog example is that neural networks are widely used in medical imaging now. So doctors get, radiologists, when they take a picture, like a mammogram, for example, there is a AI model that tells them whether it thinks that that it detects cancer or not. Of course, they're not going to base their decision on just what the AI model tells them, but it's sort of an initial indicator from which a doctor further works. So to do something like this, to train a neural network to classify a bunch of medical images as disease or no disease, for example, you need to have it labeled first. So you need to have some ground truth. Basically, you have a bunch of images which are marked as having a disease or not having a disease. But how do you get that? Okay, so some person must have gone through all of this, or a group of people must have gone through all of these images and marked them as having a disease or not a disease, and you assume that what they provided you is some sort of ground truth. I mean, so if multiple people have gone through these images and labeled them, then you have to have some way to figure out what the true label is. So learning a function in a supervised learning framework needs a labeled data set. That's what I said. And the data set is in the form of xi, for example, is image I. Yi is a label saying it's either a cat or a dog in that example, or a disease or a no disease in a medical imaging example. The question is, how do you get these labels? So that's what crowdsourcing means. Crowdsourcing is basically giving these images or inputs to different people, collecting what they think is the label for each of the images, and then using that, somehow aggregating that information to get the ground truth. So crowdsourcing, for example, as I said, so you have so there are multiple types of crowdsourcing examples. So there are things like Mechanical Turk, where people put tasks on some platform. So anybody who wants to make some money, you just pick up a subset of the tasks, which are typically images, and then you try to label them as +1 or -1, right? I mean, depending on whether it's a cat or a dog. So that's one kind of thing where you have a platform, and then you put all your images in there, and then you allow people to sort of pick whatever ones they want to label. Lots of people have, doing it independently, and then you aggregate that information. My application was motivated by a slightly different model. So one of my students, Seo-Taek, he worked at a medical imaging company in Korea for 3 years, and the way they do it is slightly different. So what they do is they take a bunch of images, let's say 1,000 images, and then they have a contract with 10 doctors, for example, and then they give these images to these 10 doctors, and these 10 doctors label each of the images as +1, -1. They look through all of the images, just slightly different from the normal crowdsourcing setup, because you're allowing people to randomly pick which tasks they want to, or which images they want to label. Not all labels will be labeled by the same, by all the workers. Okay, some images would be labeled by some workers, some images might be labeled by some other workers, because if you have 1,000,000 images, I might just take 1,000 of them to mark some +1, -1, just slightly different than in the medical setting. It doesn't really matter, but I'm just telling you what my motivation was. I mean, the theory could possibly apply to both, but I'm just saying that that's the motivation came from this sort of medical imaging company with the information that they were willing to share with us.
Is there a fit for something, or any enable any image? It's something in the doctor said, is there a specialization that they
I don't know how they contract. Probably if you're trying to label mammograms, they probably contract people who are breast cancer specialists, would be my guess. Yeah. So well, I mean, let's think of them as some sort of reasonable experts, in the sense that at least with probability greater than half on average, they would get it correct, right? That's one assumption that'll make. I'll mention that assumption later on. Yeah, there's some kind of a mild expertise assumption that we do make. Yeah. So let's take this data set. Let's say this is our data set. There are 4 workers. For example, these 4 could be doctors. The 8 tasks. The tasks could be medical images, and each doctor labels whether they think that this image indicates the presence or an absence of a disease. +1 means they think there's a disease. So for this image, for example, 1 doctor thought there was a disease in that image, but 3 people thought there was no disease. So in this example, and so for this image, 3 doctors thought there was no disease, but 1 doctor thought there was a disease. Here it is split evenly. Here 3 people thought there was a disease, but 1 person thought there was no disease, and so on. So if you're given this data set, what is the most natural thing to do? Obviously, you do a majority voting, right? I mean, that's the simplest thing to do is, so in this case, I would say that this image, the ground truth is that there is no disease here. Then the ground truth here is that there is no disease here. Here, I could choose either one. Here, I could choose there is a disease, and so on. But the question that people in who work in crowdsourcing ask is, can you do better than this? Okay, can you do better than just simply majority voting? Yeah.
Because you're getting a lot more information here, right? If doctors are very confused about a particular image, that's a very hard one.
Right. Yeah. So that's part of what I'm going to talk about exactly. How do you take that information into account? But that it's more complicated than that. So yeah. But that's one of the ideas here. There are 2 things here. So can we do better? And there are 2 aspects, right? One is that some images could be harder to classify than others, but also some doctors may be better than others, right? So that is also important. Okay. So much of the prior work only looks at this issue where some doctors are different than others. So or in the case of just, especially if you're putting things on mechanical Turk and letting people label things, some people are better than others. So let's say PI is the probability with which worker I gets something correctly. I'll get to the hard easy. That's the main part of the talk. But at this point, I'm just going to say that this is much of the work basically looks at this model where each worker has a different probability of labeling something correctly. In which case, it makes sense that you should not do weighted majority. You should not do majority voting. You should do weighted majority voting. So you should look at the label that each person gave, multiplied by some weight, which should be higher for people who have a larger PI and lower for people who have a smaller PI. And then you sum up all of this. So this would be weighted majority voting, right? And then whatever that sign turns out to be, you take that to be the true answer. So the question is, okay, so here is where I guess Mohit's question, I'm making this assumption throughout. So on average, doctors are competent or workers are competent, right? And so what should the weights be? So this is a running assumption throughout. So what should be the weights for you to get the best answer? So this model was first proposed by Dawid-Skene in 1979, before there was mechanical Turk. This was in some other context where they're collecting results from surveys, and they they actually proposed an EM algorithm, which works well in practice, but people sort of forgot about it, or not didn't forget about it, but it violently grew in popularity since the last 10, 15 years, because crowdsourcing became a thing, and then people were using it and so on. Okay. So Nitzan and Perush in 1982 looked at their model, and they said that if you know the PIs, what should be the weights? Okay, and the weights turn out to be, the maximum likelihood weights turn out to be log pi over 1 minus pi. So the closer pi is to 1, you get a larger weight, right? That makes sense. So this is a maximum likelihood estimator. As we know, maximum likelihood estimator just finds the labels that maximize the probability of of observing this data set, but that may not be the metric that you're really interested in. I mean, maximum likelihood is usually a heuristic. So the question is, what is the metric that people are most interested in? Is this. They're looking at the average error in your labels. Okay. So how does the maximum likelihood estimator perform with respect to this metric? It turns out to be asymptotically optimal. Okay, so you can get a lower bound on this error. So that's in this paper by Gao et al. And you can show that this exponent at least is correct. So if you know the PIs, then this is the correct thing to do. Okay, this weighted majority voting is the correct thing to do. Okay, if you know the PIs. Yeah.
Say an algorithm. What is an algorithm? Is it one that decides the weights?
Yes. No. Any algorithm. So any algorithms with so an algorithm is basically some mapping from the data set to labels. Okay, that is an algorithm.
And right. The data set is every task and the output of every.
Right, exactly. So in this particular case, so if PIs are known, it is asymptotically optimal. So the interesting question is, what happens if PIs are unknown? So that is what much of the work is on crowdsourcing, is what happens if the PIs are unknown.
Do you have any feedback? No feedback.
No feedback. So there is something called, okay, so at least in the medical imaging context, there is a second problem that you can work on where there is some sort of feedback, which is you might have 1 million images and you contract like 10 or 20 doctors to label them, but I mean, it'll be very expensive to pay doctors to label 1 million images. So you'd start off with labeling 1,000 images and then build a machine learning model. And then what you would do is take the remaining 1 million minus 1,000 images, run it through this machine learning model, and use that information to figure out which images are somehow harder to classify, and you take 1,000 of them again and go show it to a doctor. So that is called active learning. Okay, so there is a entire field associated with that. I'm not talking about that here. Yeah.
Right. Like
that could also be an interesting question. So
somebody right, it multiplies.
That's possible. Yeah. I haven't looked at it. I haven't seen it, but I think it also makes sense to, for example, maybe nurse practitioners are less expensive than doctors. And my daughter's a nurse practitioner, so probably she also labels things more accurately. But let's say people you pay more actually label things correctly. Then there could be a trade-off here. Whether how much you want to pay for accuracy and so on. Yeah.
In a previous result, is it assumed that each doctor, each
worker, yeah,
labels correctly with all the PI independent of
Correct. That's the most common model, is that independent of PI, independent of the image. So a doctor has a labeling probability independent of the image.
But the errors are independent for a given image.
Yeah.
But
the errors are independent. That's the assumption.
Okay. Does that really model this phenomenon that some images are more difficult to classify correctly?
That's the point of my talk. So that hadn't been looked at, so I'm going to try to figure out how to do that. Yeah. So far, much of the work doesn't take into account that some different images are harder to classify and easier to classify, right? So mostly this is. I mean, this actually, it turns out that for many data sets, even just going from majority voting to, I guess the way to think about it in all of machine learning, there is a trade-off. The more you model, you might get better results, but also you might generalize worse in the sense that the more parameters there are in your model, so it's a trade-off, right? So these models assume that there's just a small number of parameters, which is one associated with each worker. The more, so there are models actually which looked at for every image, there is a Pij, which is different for each image. There is also a model like that. We tried some experiments on those, and using those models, you get much poorer results, even though that's a more detailed model, probably more accurate in practice and stuff like that. But given the data that you have, the generalization performance of those are really bad. Yeah.
Yeah, but so on this independence assumption that
well, let's because I'm not so I'll go to a more detailed model, and then we can have that discussion, okay? Because at this point, this is just what people do, and this actually does better than just simple majority voting. That is the main message. But I'll get to a more detailed model, which actually turns out to be better, where some tasks are easy, some tasks are hard. Okay, yeah. So where was I? Yeah, all we have is the observation matrix. So what do you do? So I'm not going to talk about this work, but just for background, what people do is first estimate the PIs from the data itself. Okay, so there are some spectral ways of estimating the PIs. By looking at the matrix and looking at some eigenvalues and eigenvectors associated with the matrix, you can actually estimate the PIs and then substitute it in the Nitzan-Perouche formula. And then that's most of these workers in that spirit. EM algorithm works very well most of the time, but it's hard to analyze. So there are many other algorithms that people have studied. They all actually are asymptotically optimal and give good results, okay? So what I am going to do is look at a model where some tasks are harder to classify than others. So what I understood from Seo-Taek is that in this company, they've noticed that the size of the nodule is very small. Then it's harder to tell whether there's cancer or not, for example. Okay. So therefore, we use a extended Dawid-Skene model. Basically, we assume that there are two types of tasks, hard and easy. And worker I labels a hard task correctly with probability HI and an easy task correctly with probability EI. So this is addresses Swati's question at least. So basically there are two types of tasks, hard and easy, and hard tasks. So doctors have one probability of classifying hard tasks and one probability of classifying easy tasks, okay? But we are even allowing that for some doctors, some images may be harder to classify, for others, some other images may be harder to classify. So the assumption we make is that this vector REI, which is called the reliability. So the REI, so the scalar REI is simply 2 times PEI minus 1. So this is for the ith worker. This is the reliability with which this quantity is called reliability. 2p minus 1 is called reliability. So this quantity, this vector, so REI is a value for each worker I. So if you stack them all together, it's a vector. So I'm going to assume there are two types of tasks. The norm associated, the norm of reliability is associated with one type of task is larger than the norm of reliability is associated with the other type of task. Okay, so this is the model. So the question is, given that we have a model now that some tasks are easy, some tasks are hard, how do you solve this problem? So as before, as always in many of these problems, it's easier to assume more data, more information than you have. So right now we just assume that you have an observation matrix. Let me add more information, see how I would solve the problem, and then go back to solving it in a data-driven fashion. So now I guess your question was, what happens if it's correlated, right? I don't know how to model that yet. Yeah.
It's correlated in a scheme such as first find out if it's easy or hard, and if it's a hard one, put in some extra effort.
Yeah, that's exactly what I'm going to do.
Such a scheme didn't know the previous independence assumption doesn't seem to make a difference.
Right. I mean, these are all assumptions, right? I mean, we don't know what the truth is. So it's like all machine learning models are like, you don't know what the truth is, right? I mean, it's just a model is a model. And the less complicated a model is, you're not going to model reality as well. But on the other hand, it'll give you better answers if the data set is relatively small. So that's always a trade-off, right? So here, given this model, so what I'm going to do is we'll assume more information, try to solve the problem, and then finally I'll show you what the solution is in a data-driven fashion without knowing this additional information. Okay, so let's pretend that somebody has told me that these are hard tasks and these are easy tasks. Okay, then what would I do? So basically I would separate the hard tasks, okay, separate the easy tasks, apply one of the standard Dawid-Skene algorithms for the hard tasks and one of the standard Dawid-Skene algorithms for the easy tasks, and do it separately. But we don't know which the hard tasks are, which the easy tasks are. So what do I do in this case? It's interesting that we just looked at O. So if O is the observation matrix, then you look at O transpose O and take the expectation. So you're pretending here that I know PHI and PEI. Then I can write down the expectation. I know exactly what this matrix is. This matrix turns out that you can easily see from the expressions this matrix has rank 2. Not only that, the principal eigenvector looks like this. All the entries corresponding to the hard tasks have one value, and all the entries corresponding to the easy tasks have a different value. Okay, so then what should you do? It's obvious, right? You just remove the expectation because I don't know. I don't have the expectation. So I just use the observation matrix, do O transpose O, look at the largest eigenvalue, and then apply this, and then basically cluster them. So this should be the algorithm, right? I mean, this is the most natural thing to do. I don't have expected value for transpose, so there's a 1/n scaling to make it look like law of large numbers. But and we would need that when you do concentration inequalities and so on later on. So you look at the principal eigenvector of O transpose, so without the expectation. So we made this observation. I mean, I didn't show you all the calculations here, but it just be some ugly expression involving PE and PH and so on. But basically, if you look at the largest, the dominant eigenvector, it'll have this structure. So now I just do the same thing without the expectation. And then what should I do? So I have to do clustering, right? I know that all the hard tasks will have one value in the eigenvector, and all the elements corresponding to the easy task will have a different element. So the most natural clustering would be to take the average of all of this, okay, and then you know, if it's on one side, say it is hard, and if it's on the other side, say it is easy. This is clear. Yeah.
So what is the expectation of O transpose O means? How is it defined?
So this is O. This matrix is O. Here with probability PE, you label it correctly. With probability 1 minus PE is correctly. So this will be the ground truth with probability PE. With probability 1 minus PE, it's not the ground truth. Okay. Right. And so based on that, you can calculate all of this. So all of this will actually get multiplied by the ground truth. So I didn't say that. So this is, all of these will be equal in magnitude, but there'll be a plus minus sign difference because of the ground truth. Is that clear?
Earlier we had a PEI.
Yeah, PEI for each.
So is there an expectation of PEI over the I's?
No. PEIs are just the probabilities.
But here you said PE. I
mean the vector PE. So the answer will be in terms of the vector PE, PE1, PE2, PE3.
What is N and your expression for?
N is the number of workers. Sorry. N is the number of workers.
So you do the average over the work.
I do, just because later I want to relate this to expected value of O transpose O. You don't need to for this algorithm. You don't need to, just that otherwise everything will be large numbers. So you just, for convenience, you just divide it by N. But the structure will remain the same. I mean, the fact that some of the eigenvalues, there'll be two non-zero eigenvalues. You take the one corresponding to the largest eigenvalue, look at the vector, all of that will be the same. This N is just for numerical stability in the algorithmic part. Because otherwise you're multiplying and adding a whole bunch of things. So you don't want it to scale with N and blow up on a computer. So you're just dividing by N.
Why do you classify the task into hard and easy?
Because then I can apply the standard algorithm. So the original algorithm assumes all of the tasks have the same probability of labeling by a worker. So now I'm assuming there are two types of tasks. One are harder and one is easy. So they have different probabilities. So I'm converting it to a standard problem. Once I classify, I can just use one of the existing algorithms like a black box. Is there another question? Yeah.
Yeah. Out of curiosity, typically how many tasks do you have such number of workers?
That varies. So we looked at two data sets, one data set about 20 something, other data set about 60, 70 workers. Yeah.
And the number of tasks?
It'll be in the experimental results. I don't remember exactly. Thousands, maybe. Yeah.
The matrix that you should identify for is task by task or worker by worker.
It will be O transpose O. So this will be task by task, I guess, right? Yeah. Yeah. Yeah.
So we have to go to class right now, but does it generalize to more than two categories?
You could, but that is again a trade-off. I mean, the more categories you have a more complicated model. You have to estimate more things. So it's just like in any machine. It's like whether if you have a bunch of points, are you trying to draw a straight line or a quadratic? So it is like that trade-off. Yeah. So, yeah. Okay. So in a simple example, so in this example, I have 2 workers and 4 tasks. So just to run through the algorithm quickly. So first I look at the O matrix, do O transpose O. In this case, the number of workers is 2, divide by 2. And then you look at the largest eigenvalue. I pick those numbers so that you can see that these 2 tasks are of one type and these 2 tasks are of another type. Okay. In reality, of course, it'll be noisy and it won't cluster like this. But just to illustrate, so here in this case, these 2 would be easy tasks and these 2 would be hard tasks. And what I would do is, since I know that this and this are easy tasks, I would group them together and apply as the standard algorithm. And then here again, I would apply the standard algorithm for the hard tasks. So is the algorithm clear? Okay. So here are some theoretical results. We show that the probability of making errors in identifying hard and easy tasks is given by this formula. And for tasks that are estimated correctly, so basically this is saying that number of tasks that are misclassified is small. And this is saying that the number of tasks, given that the task is classified correctly, then getting its label correctly is also will be small depending on n. Okay, and you can put these together to get an overall error bound. Okay, of course, this doesn't. I'm not expecting you to understand this to interpret this. So in the next few slides, I'm going to interpret the result. So when will it be easy to classify hard and easy tasks? So there is a reliability vector associated with the easy tasks and the reliability vector associated with the hard tasks. Okay, it turns out that if these reliability vectors are right on top of each other, then of course it's harder to classify unless their magnitudes are very different. So either the magnitudes should be sufficiently well separated or the angle should be well separated, right? Then this k that I have is actually a function of both the angle and the difference, the angle as well as the difference in their magnitudes. So you can see that as this thing becomes separated or the magnitudes are different, so in fact, it's exactly a function of norm of RE minus norm of RH divided by the inner product of the two. That is a very nice interpretation. And then for tasks that are estimated correctly, it turns out that, of course, it's going to be easier to label easy tasks, and it's going to be harder to label hard tasks. Even once you figure out these tasks are easy and these tasks are hard, by definition, hard tasks are harder to label. So therefore, you cannot, so there will be an error rate associated with hard tasks, error rate associated with easy tasks. They will be different, but this comes from standard prior work. Okay. But an interesting question to ask in this case is that what happens if you don't do what I just said? Let's just say you're going to use some weighted majority voting with some different weights. So somebody says that I have an algorithm that does weighted majority voting. You don't have to classify hard tasks and easy tasks separately. So the question is, what will be the performance of that algorithm? So you can easily make up an example where if you do that, you will do worse. So for example, here is an example where worker 1 finds this task hard and this task easy, but and similarly for worker 2, it's the other way around. but the norm of the RE and the norm of RH satisfies the assumption that I meant. On average, the easier tasks are easy and the hard tasks are hard. But it's not, as I mentioned earlier, that's not true across all workers, right? This is some sort of an average definition. So using that, you can argue, so that's sort of the intuition. What you can show is that if you use a single weighted majority voting algorithm without separating hard and easy tasks, there is some expression. But I guess the main point to show, the main point to argue is that what we can show is that the rate at which the probability of error is going to 0 using a single weighted majority voting will be sort of will be the hard tasks will be the bottleneck. So basically, because hard tasks will mess up both the estimation of the hard tasks as well as the labels for the hard tasks and the easy tasks. It's clear. What I'm saying is because you're mixing the two and trying to find the best labels, the presence of hard tasks makes the estimating the label even for the easy tasks hard. So this is what the math tells us. So the asymptotic, the exponent, if you try to do a single weighted majority vote without separating the hard tasks and easy tasks, there's no way it'll do as well as separating. This is the message. Yeah.
What is the single weight here?
It doesn't matter what the weight is. So this result is universal.
For the best possible weight.
Yeah. So let's say somebody says, I mean, the standard thing in practice is to do weighted majority voting, right? So you could ask the question. So what I'm saying is that so you're given a data set. I mean, who knows what the truth is, right? I guess. Yeah, this is the data set. Who knows what the truth is? I don't know whether they're hard tasks, easy tasks, or whatever, right? I could just apply the Dawid-Skene algorithm to this model. It'll figure out, it'll do something. The original Dawid-Skene algorithm is just a simple weighted majority voting algorithm. I could just apply it to this. It'll figure out some weights. I mean, it's an algorithm after all. It'll find some weights. It'll just do this. What I'm saying is if you do that, it won't do as well as what we are suggesting. That's all I'm saying. But the result is over any possible. It's not even applying the Dawid-Skene algorithm. It's stronger. It just says that whatever, so let's say allow you to do a weighted majority voting, whatever you do, however you choose the weights, it can't be as good as separating hard and easy tasks. This is the result. Okay. Yeah, so they're saying that a single type DS algorithm can never do as well as separating hard and easy tasks. Of course, these are all asymptotic results. If n is very small or d is very small, some of these things will break down. Asymptotically, this is true, right? So there's a practical question. If you don't have small n and small d, for example, maybe it's better to do a single Dawid-Skene type of algorithm. That's an open question. I'll mention that later. How to? It's not quite. It's an open question, but we have a heuristic that sort of seems to do always better than separating or not, but I'll get to that. But theoretically, this is all we can show. And this lower bound is just a standard Chernoff, a Kramer-Chernoff kind of proof. So I don't have much to say. Yeah.
So in general, you can also have multiple sets of tasks, so just easy and hard. You can have.
Yeah, exactly. But as I said, this is always, it's like you're given a bunch of points, are you going to fit a straight line? Or whether you're going to fit a second order polynomial, third order polynomial, fourth order, the larger you do, of course, you'll fit all the points, but you'll also be misestimating things poorly. Exactly the same principle applies to any machine learning model. The more complicated the model is, you will fit the data, but it won't generalize very well. So here, I'm just saying that there is an advantage from going from 1 to 2 based on the data sets that we have observed. Okay, so in a practical problem, in this medical imaging company, what they have noticed is that small nodules are hard to detect even for doctors. Bigger nodules are easier to tell whether there's cancer or not. So that was sort of the motivation. Now there are different sizes of nodules, of course, based on that, you should be more, the more complicated you make the model, you won't get anything useful out of it. I guess that is the point. Just exactly, it's no different than when we did Hooke's law experiments in high school in physics, attach a weight to a spring and trying to figure out Hooke's constant. You try to draw a straight line, right? You don't try to draw some higher order polynomial. even though it will never fit. Although some of my friends first put the points and drew a straight line through them, but in practice, you can't really fit a straight line, of course, because of the noise in the measurements, right? So this is a synthetic experiment. Before I give you the actual some real experiments, this is a synthetic experiment that my students did where they varied the angle between RE and RH. As you can see, that as the angle increases, the prediction accuracy increases. Of course, each experiment, of course, you'll have some noise, but if you look at the overall average error, it sort of clearly is better to have more angle between RE and RH. Similarly, you can also have perform experiments where the norm of RE and RH is large. So it's, I mean, two vectors are different. As long as the angle as well as the norm are not the same, they're of course going to be different, but the more different there are can be measured in terms of both the norm and the angle. And here it's a plot for angle. You have a similar plot for length also. So we compared our algorithm, basically separate and then apply one of the standard algorithms. There are many standard algorithms that people use in the literature. People still use majority voting sometimes because it's just easy, right? So just for comparison, we use one of the existing algorithms. These, of course, there are hundreds of algorithms. This topic has been so popular, there are literally hundreds and hundreds of papers, each one having its own algorithm. There's no way to compare to all of them. So we sort of looked at papers that say that my algorithm is better than these other algorithms, and they eliminated those algorithms from assuming they're telling the truth. So we reduced it to 4 algorithms to do a comparison. I don't know how to compare to all of them.
So again, like, can you just tell us like how, like this is synthetic data?
This is synthetic data. I'm going to get to real data.
But like how do you kind of like generate the data?
So basically, I don't remember what the number of workers. So basically, assume some PE/PH model, okay, and then you assume a ground truth label, and then you flip a coin to decide +1 or -1. But the PE and PH were varied so that the angle between the RE and RH vectors get larger and larger, and you can see the prediction accuracy gets better and better.
So here you kind of assume the graph.
Yeah. This is just to test that everything makes sense. But this is real data. So this is a data set with, I think the 20 is wrong. I think it's like 25 or 27 or something like that. So it's 20 workers and 200 images here. And so what am I trying to say here? Yeah. So this is, for example, if you don't separate the hard and easy tasks, for example, the TE algorithm, which is the best here, gives you an error rate of 4.74, okay? Whereas our algorithm reduces the error rate to 3.16. So the better algorithm you use for, all of these are algorithms for the single task type Dawid-Skene model. On top of that, if you don't separate them, unseparated and separated. If you separate it, improves. But the improvement is not huge when you have 20 workers. The improvement is much more significant when the gains are much more significant. For example, there's a 28% when the 30 in this data set, the 39 workers and 100 tasks and 78 workers and 800 tasks in this data set. So the number of workers increases. I think the being able to separate hard and easy tasks is easier, which makes sense because you could look at all the workers' labels and that, if they're all similar, then of course it's easy. If they're all very different, then it's harder. But of course, it's more complicated than that. But that's the intuition. So the more workers you have, our algorithm will perform even better. But the flip side of all of this is that I should also tell you that if the number of workers is small, maybe one should not separate. So this goes back to the question that multiple people have asked me, why not have more complicated models, right? When the number of workers is small, that means the data set is small. You should not use more complicated models. The simpler model will actually give you a better result. So we have, I think we are going to put up our paper on arXiv with some additional experiments where we show how to combine our algorithm with existing algorithms, that heuristic to perform better. It's a heuristic combination to perform better than both. So in practice, we don't know at what number of workers does the separation algorithm perform better than the unseparated algorithm. And this is exactly like the physics Hooke's law kind of thing. Do you fit a straight line or higher order polynomial? Yeah.
For the
the pneumonia experiment, what do you consider a crowdsourced label?
Well, there is a data set which people used to be, say it's ground truth. Yeah.
Basically consider the majority vote?
No. Somebody put up a data set. So this is a standard data set that people use to evaluate these algorithms. The data set we are assuming is ground truth. Somebody has that label is ground truth. Somebody has done a lot of work figuring out a good data set where they know that this is ground truth. And yeah. So I think, in reality, you first make a decision probably as a doctor. I'm not a doctor, so I'm making this up. I would think that you look at an image and make a decision whether somebody has this disease or not. But then later you treat them, and over time you probably see how they respond to the disease and know for sure if they have the disease. You probably won't just base it on just the medical image, right? You'll then do a blood test, you'll monitor them, blah, 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 and then maybe decide. So the ground truth is probably derived looking at, yeah. So I don't know how they came up with it. I'm just assuming that
This is challenge, especially in pneumonia. About this is that you have labels from multiple people, but there is no way of it.
Yeah, exactly. That's what crowdsourcing does. So crowdsourcing, so that this is just for experimental reasons, but in practice, what we will do is we will extract the label using this kind of an algorithm. The simplest thing to do is majority voting. The more complicated thing to do would be weighted majority voting. And again, it's all a matter of how much data you have. If you have very little data, maybe majority voting is the best thing, because you assume nothing about the model. The more you assume about the model, you will get better results if you have more data. So this is always a trade-off, and this is a hyperparameter selection problem in machine learning for which there is no real answer. It has to be done on a case-by-case basis with some kind of expert knowledge. There's no way to know for sure whether your algorithm, what you're doing, is the correct thing or not, right? Yeah, and that's why obviously nobody would. So this institute that Sivateja talked about, this Digital Transformation Institute, one of the people we fund, this institute, half of the money is used to organize seminars and workshops and conferences and stuff. Half of the money is actually used to fund people to do work on machine learning. One of the people we fund is a very famous person from University of Chicago. She is one of the first people to use AI to diagnose the presence or absence of cancer in a mammogram. So when I talked to her, she said, she has been working on this since 1998, and her products are used by doctors all over the world. But nobody is going to use her product as the only. This is just, the product is going to tell you, I think there is cancer, but as a doctor, it's your responsibility to come up with the final answer, right? This is just an assisting tool. So yeah, there could be errors. Depending on what assumptions you make, whether you're doing majority voting, weighted majority voting, whether you separate them and then doing weighted majority voting, all of them will give slightly different results, right? So this is where I think we came up with a heuristic which seems to actually work well. So what we did was we ran multiple experiments, or ran under multiple assumptions. We came up with a label. And if all of them said that this is the same, this label is, if all of the methods came up with the same label for a particular image, then we'll assume that to be the truth. So it turned out that actually for 80% of the images, it does that. For the remaining 20%, we went and did some more work. And then we repeatedly did this a couple of times, and actually that produced a better result than any algorithm. Yeah. So. Okay, so let me just briefly give you the intuition behind the main theorem that I mentioned. So there are two parts of the theorem, which says that, for those of you who are interested in this, these are tools that are very standard tools, but for people who have not seen it. So there are two types of error here. One is the probability of classifying a task as hard or easy. Another one is, once you classify a task correctly as hard or easy, then the probability with which you get the label correctly, right? So how do you obtain performance bounds for models like this? So I got my intuition by looking at expected value of O transpose O. But really what I have is O transpose O. So the difference between these two I'm calling noise, right? So I want to get a handle on what this noise is, right? So I've already said this. So there is something called the Davis-Gahan theorem, which many of you may know. Davis-Gahan theorem is a theorem on perturbation of matrices. If you take a matrix, perturb it slightly, how will its eigenvectors and how will its eigenvector change, right? So the Davis-Gahan theorem says that if the foo norm between the largest eigenvalue of O transpose O and the largest eigenvalue of expected value of O transpose O is upper bounded like this, where this is the largest eigenvalue. This is so basically it expresses the difference, the norm of the difference between two eigenvectors of two different matrices in terms of the eigenvalues of one of the matrices. So in our case, the matrix that is easy is the expected value of O transpose O. So all of this can be computed, right? And this is something that I cannot compute. So what should I do with this? I had to do this to compute the difference between O transpose O and expected value of O transpose O. I should use concentration inequalities. So the denominator is something that can be computed. To be further upper bound the numerator using concentration inequalities. And so we use the matrix Bernstein inequality in particular and get a characterization of this error. And we can put the two together to get this result. Yeah. And when we do this, this K turns out to be an increasing function of this quantity, this norm of RE squared minus RH squared divided by the inner product. As I mentioned, if the norms of these two vectors are very different, then we get good results. And if the angle, if RE transpose RH is close to 0, they're perpendicular to each other, then also you get better. It's easier to separate the hard and easy tasks. So it's very intuitive. So I was very glad that we got this expression and we couldn't figure out what it looked like. We kept working on it, and finally we were able to massage it into a form where this showed up very clearly, and then felt like, okay, this must be correct. Yeah.
What is lambda? Can lambda 1 be equal to lambda 2?
No, in this case, it's not.
So what are these cases? I mean, can that happen in practical situations?
No, it cannot. In my model, it cannot happen. Yeah. I mean, I don't know what you mean by a practical situation. So what I mean is the Davis-Gahan theorem just says that if lambda 1 and lambda 2 are separated, this is the answer. Right? So if there are problems for which, I don't know, maybe there's a way to look at the third eigenvalue. I'm not sure. So conclusion is that so the main contribution here is that we extended the Dawid-Skene model to allow two types of tasks, hard tasks and easy tasks, but of course you don't know which the hard tasks are and which easy tasks are. So we came up with a spectral clustering algorithm, and we were able to show that our algorithm will always perform better than an algorithm which does not do separation when there are many workers. Now, where that cutoff is for many workers is something that doesn't seem easy to figure out from the data itself. So I think you probably have to come up with some heuristic to do better. But if there is a way, maybe a data-driven way to figure this out, that would be an interesting open problem. And also for the clustering step, even though we proved that any weighted, so I guess I should say that it's provably better than any weighted majority voting algorithm. Okay. But I don't know if this actually achieves some minimax bound or not. Okay, so for the single task type case, you know that it achieves a minimax lower bound. In this case, we don't know if it achieves a minimax lower bound. And the reason is that we don't know whether the clustering step that we have is whether that is the best algorithm, whether the spectral algorithm is better than this. I was talking to one of your colleagues in the math department. Yeah, Chen Ma. Yeah, Cheng Mao. He has worked a lot on this, and so I was asking him, and it doesn't seem at this point I don't know the answer to that, whether the clustering algorithm is the best that you could do, or because in some cases you can do better than spectral clustering. You can do message passing, you can do something called non-backtracking, random walks and things like that. So I don't know so that is the bottleneck in proving that this is asymptotically the best algorithm. So we compared it to so it performs better. We can prove it's provably better than any existing algorithm if there are hard and easy tasks. But whether it's provably better than any algorithm, I don't know. That's a interesting open question that I'd probably like to think about more. That's it. Thank you. Yeah.
Maybe a naive question, but why are we trying to create 0-1 labels in the first place? If we know that we're going to learn afterwards, why don't we just try to learn the ratios first?
Try to learn the what?
So just try to learn the percentage of people who do +1 and the percentage of people who do -1. So I feel like at this point.
Yeah, you could also, that is also part of the algorithm. The algorithm actually learns that too. Ultimately, to train a machine learning model, you need the labels +1, -1. To train a machine learning model. So if you want to put this in as input to a neural network, you could do that. But if you want to come up with your own algorithm to, if you're using the probabilities, you're welcome to, because we do that as part of the algorithm. So we estimate the probabilities as part of the algorithm, because we need this. We stick it into this Nitzen-Perush formula. So first we have to estimate the p. I didn't talk about estimating the p because that's not our contribution. That's sort of a well-known. So I just talked about how to separate the hard and easy tasks. Once you separate the hard and easy tasks, you do estimate the probabilities before you get the labels.
So what I mean here is, rather than having an in-between step of trying to find out the true label for all of the tasks, we do some other sort of machine learning that doesn't only predict 0-1, but can actually predict the probability of being 1.
Yeah, you could do that. I mean, that's yeah, sure. Yeah, I'm not saying you can't do that. I think the way, at least the way these companies work, is that they have a neural network and they want to give input to the neural network. The input to the neural network today is +1, -1. But of course, if you have teacher-student models, there are all kinds of things where you can give soft labels also. Yeah, that could also be a possible. Yeah, so that's a possibility. That's a good question. Maybe I didn't go to the next step of how we are going to use this results. You could potentially have soft labels and then give that as and train a neural network using soft labels. That could work too. Yeah, or could work better, like you said. Yeah.
There's something beautiful about the way you separate the tasks, which is that I find very beautiful. You don't assume anything about what is a hard task or an easy task.
No.
Right? You look at all the labels together, and then the spectral approach.
Right.
And you get, this looks like hard, this looks like easy.
Right.
Which kind of goes against my intuition that there should be some intrinsic property of what makes a task easy or what makes a task hard.
Yeah, so there is a, go ahead.
The question I want to get to is, if you do all this and you identify what are the easy tasks and the hard tasks. So say you have 1,000 tasks, you label all of them. And now you have 1,000, you have one extra task, and you get the labels from all the workers. Can you tell me whether that's an easy task or not? Or do you have to redo the whole spectral estimation?
I mean, you could come up with the maximum likelihood estimator, because you would have calculated the P and pH based on that, based on what you had, and you could use a maximum likelihood estimator to estimate whether the new task is hard or easy. I haven't looked at the asymptotics of how accurate it'll be, but you can do that. If I know P, pH, I can use maximum likelihood estimation, right? Yeah, but it's an interesting question. Whether that's the best thing to do or whether to go back and look at the whole matrix again and do it, I don't know about that. But you can do it. There is an answer to that.
If this is eigenvalue based, you can probably do like rank 1 correction and then.
Yeah.
This way of playing it.
Yeah.
But I was wondering if there's like a.
Yeah.
For explicit formula that says, now this is in the space of labels. This is what it has.
I mean, since after I separate the tasks into hard and easy, I would calculate this for the workers, the probability that a worker estimates the hard task correctly and estimate the easy task correctly, right? I know these probabilities, that I have estimates of these probabilities. So now if you give me a new vector, I can see whether it was labeled, whether it was an easy task or hard task by looking at the likelihood of seeing that observation. And based on that, I can try to do something. Yeah. Yeah.
Like the last thing you said, like where does the number of workers show up, like as one, like you said, like
N is the number of workers.
Okay, and if
D is the number of.
There, you're saying this quantity could be worse than the one you would get using the other. Like theoretically, also.
If N is very small, this could be worse than the than if you just assume so one task. So experimentally, we see that actually.
That's right. But it just shows up. The theoretical bounds are
correct. The theoretical bounds only are accurate when n is large. Yeah. Yeah. We have an yeah, so we will have okay, we need a lower bound on the probability. Yeah. Correct. Yeah.
So the follow-up to the hardness of the task. So would it make sense to sort of consider, say, features of tasks that will make a task hard or
That's possible, but then you'll have to examine each image then to so you've already asked people to label these things. Maybe, yeah, we did think about this question. That's a good question. Yeah. So we did think about the following enhanced model where we ask each doctor to tell us whether they thought this task was hard or easy. Okay. Let's say they also, in addition to giving a label, they say, okay, this was hard for me or easy. Then you could possibly use that side information to actually do even better. That's an interesting, I mean, I'm interpreting your question that way, but yeah. But then we have to think about a model for when they would say, whether they would correctly say it's hard or easy or whatever. But yeah, I do think that would help the doctor themselves say, okay, this is hard or this is easy. Or maybe ask them to rate it on a scale of 1 to 10. Was this image easy for you or hard for you? Maybe that information can be further used. Yeah.
Because like why I asked this, like I follow up to that, like the individual tasks are correlated, like the classifications across various doctors that are correlated, right? So in this model, at least directly, there is no way to capture this correlation.
Correct.
But if there are some features through that, this
Sure. That was, I guess, one of your colleagues was asking this question. Yeah, exactly. Yeah. You could, if the easiest thing would be to ask the doctor to tell you, I think, and then I think then you can see some correlation. If all of them are in a scale of 1 to 10, if many of them say that it's like 7, it was hard, then you probably have some side information that's hard, and you could probably use that. Yeah.
Let's thank Srikanth again.